Hello, my name is Helena Moore, and I will be presenting the first part of the Stat 61 final project, the data set background and description, as well as the data preparation and summary. So our topic for our project was predicting heart failure mortality, and the authors were Kevin Zhao, Helena Moore, Angela Lee, and Zan Siddiqui. So about this data set, our data set comes from the authors David Chico and Grisep Urin. These were two individuals who created a data set that could be used to predict mortality rate of patients who had heart disease and the corresponding risk factors for heart disease. So this data set is very relevant to today's society because currently cardiovascular disease is the most common cause of death in the world. It takes around 17.9 million lives per year, which is 31% of all deaths in this world. So obviously we were motivated for choosing this data set because it really opened our eyes to the magnitude of this issue. And it allowed us to look at real life examples of the danger of cardiovascular disease and the mortality that it causes. This data set is important because it can be used for early disease detection by telling patients their likelihood of dying if they have a collection of these variables and certain levels. So these variables that can be used for disease detection include anemia, the presence of high blood pressure, their sex, their age, and certain risk behaviors such as smoking. Other variables in this data set include measures of factors in the blood such as serum sodium levels, serum creatinine levels, which is a measure of how well the kidneys are working, as well as ejection fraction, which is the percentage of blood leaving the heart at each contraction. So, for example, for ejection fraction, for a normal heart, it should be between 50 and 70%, but if it's under 40%, then there is a risk for heart disease and heart failure. So when looking at all of these variables together, just when certain levels in the blood are right and when risk factors are present, there's just a much higher risk of mortality. So for our data wrangling and relevant variables, when we cleaned up this data, we really wanted to investigate the effect of the factors of age and gender. So we were subsetting a lot for gender for a lot of these variables because the two sexes have different levels of things such as serum sodium levels that they can withstand. So men will have a higher range that is safe for them, for example. So additionally, we mutated columns and created another data set for numerical variables where we averaged each numerical variable based on each age group in order to look at the average levels per age. Additionally, for our numeric variables and our serum levels and ejection fractions, we translated those in another column by mutating them into ordinal categorical risk levels. So for example, a creatinine level of 0.74 is at risk and below that is not. So additionally, we removed the time column, which was the time after treatment or the follow-up time, because it was not relevant to predicting the likelihood of death. In fact, it was the other way around. The likelihood of, or the event of death had an effect on the time, because if a person died earlier, then their time would be shorter. And additionally, the time was not relevant because a person could die immediately after the time. So as previously mentioned, we were subsetting a lot for the key variables of age and gender, just based off gender differences in the body. And we were very interested in how age affected mortality. We also separated this into looking at each risk behavior and risk factor, such as diabetes. And we were also interested in looking at what the serum levels and ejection fraction showed, and really translating those numeric variables into understandable visualization for our data.
All right, hello, my name is Kevin, and for this segment of the project, I'll be going over summary measures, two-way/frequency tables, and a data visualization. So first, I'd like to go over our two-way/frequency tables for important categorical variables. So for our two-way tables, all of our variables here are binary, so meaning their data is like no or yes, or alive or dead for status, gender, female or male. All of these are binary, and they will show the counts for each. And for our frequency table, we have a sodium risk level here, where it shows an individual's risk level and their counts. And then for age, we couldn't fit all of our data here for our frequency table. So instead, we decided to do a summary measure where it summarizes the mean, median, mode, min, max, and the quartiles. Moving on to our summary measures for important numerical variables. Here we use a summary function in R to summarize mean, median, min, max, mode, quartile, and standard deviation for all of our numerical variables. Next, moving on to data visualization. Here, I'd like to start with our bar graphs. So for our bar graphs, we decided to split them into two groups based on their life status. So one group would be everyone who is alive, and another group would be everyone who is dead. We did this so we can show the differences between the categorical variables of those who are dead or alive, which could give us some clues on how these factors can play into heart failure. And by these factors, I mean anemia, diabetes, high blood pressure, and smoking, which are all common factors to heart failure. And here are the bar graphs for those who are dead. They're the same factors, as you can see. And for our stacked bar graph, we decided to make the stacked bar graph on the left showcase creatinine risk by age to depict two categorical variables, and visualize people who are at risk of heart failure because of creatinine levels for each age group. And so here it looks like 60-year-olds are more at risk than any other age group. And our second stacked bar graph actually shows sodium risk by age. Sodium risk of heart failure by age. These two graphs allow us to visualize which age groups are the most at risk for heart failure due to creatinine and sodium levels, which after some research, these two factors, sodium and the creatinine, are actually very related, very correlated towards heart failure. And moving on to our histograms. Similar to our bar graphs, we decided to separate our histograms into those who are alive and those who are dead. This way we can more accurately depict the distribution of ages and draw more accurate conclusions based on them. And based on these histograms, we can actually see that the 60 age group here has more fatalities than any other age group. So moving on to our scatter plot, after some research we decided to create the scatter plot depicting the relationship between creatinine phosphokinase levels and creatinine serum levels, because they actually have a scientific correlation with each other. But looking at the actual plot, we see that the points lie in the bottom left corner and hugging the two axes. Because of this, there isn't any positive or negative or any statistical correlation between these two variables that we can see. And moving on to our box plots. So the box plots on the left depicts the effect of sodium serum level on life status. So we wanted to visualize the level of sodium serum affected. We wanted to visualize how the level of sodium serum affected one's life status. And here we can see that those who are alive actually have a higher sodium serum level than those who are dead. And moving on to the box plot on the right, we wanted to depict the effect of creatinine serum level on life status by age group. So this graph actually shows two categorical, status and age, and one numerical, which is the creatinine serum level. Here we wanted to visualize how creatinine serum levels affected life status, similar to the box plot on the left, but also show the ages to get a better breakdown of the levels of how creatinine serum levels for each age group and what their ultimate life status is. So basically we can see more in depth of the box plot rather than just one categorical and one numerical variable on the left. Moving on to our final graph, which is our heat map. This is our special graph. It shows the amount of platelets by age and life status. Heat maps allow us to see the concentration of platelets for each age group, as well as their life status. So we can see actually if platelets are a factor for heart failure by looking at this, by looking at the colors here, seeing the concentration, the amount of platelets for each age group. And also we can see what their ultimate life status is if they're alive or dead. And looking at this graph, there doesn't seem to be any extreme amount of platelets for any one age group. So we don't see any like blue or green colors on here. So yeah, that should be all the data visualization. And Angela will talk about 1 and 2 sample inferences next.
Hi, I'm Angela Lay, and today I will be talking about 1 and 2 sample inferences. Using key variables in our data set, we were able to make both a 1 sample inference and 2 sample inference of heart failure. For our 1 sample inference, we decided to use a confidence interval to test the average age of the patients that died. We ran a 1 sample t-tested means and used the subsetted data death-dat and the age column with a 95% confidence interval. This led us to our interpretation, as you can see on the slide below. We are 95% confident that the average age of patients that have died is between 62.53776 and 67.89280. This 1 sample inference shows us that patients between basically ages 63 and 68 are more likely at risk of death than other ages. Now, for our 2 sample inference, we just also used a confidence interval. We decided to test whether or not women have a higher proportion of death compared to men. As you can see on the slide, population 1 was female and was represented by PF, and population 2 was male and represented by PM. This made the confidence interval PF minus PM, population 1 minus population 2. Using the gender count table of patients who are alive and dead we made in our data cleaning section, we found that there were 34 female deaths and out of 105 female patients. There was also 62 male deaths out of 194 male patients. With this data and a 95% confidence interval, we ran a two-sample prop test of proportions. Since this showed us that the sample estimates of females was 0.323895 and the sample estimates of males was 0.3195876, we calculated that the difference between them is greater than 0. This led us to conclude that females have a higher proportion of deaths than men. With the two-sample prop test of proportions, we could also see that the proportion of deaths for women is between negative 0.1109794 and 0.1194232 higher than men. Next, we will be talking about regression.
Okay, hey guys, I'm Zan Siddiqui. I will be presenting our last part of the Stat 1601 final project. This is a regression part. Okay, so, okay, sorry about that. Okay. So we decided to create a multiple regression for predicting the creatinine serum and sodium serum levels because there's multiple predictors that correlate with both of them. So specifically creatinine phosphokinase, platelets, and ejection fraction decimals are variables that contribute to predicting both both levels. For the predictor data set, we set the creatinine phosphokinase equal to 2,000, and the platelets equal to 230,000, and then the ejection fraction decimal equal to 0.35, as you can see in this slide, which the original numbers to predict the creatinine and sodium levels. For our creatinine levels, our prediction bounds were between a negative 0.66 and 3.44, which is a pretty large range, as you can see, but could be due to error in the data set. Using these predictors, we can be 95% confident that the creatinine serum level will be around 1.38 approximately. So on this slide, you can see our intercept is 1.546, while our coefficients for creatine phosphokinase is negative 1.66, negative 1.688 times 10 to the negative fifth. The platelets is negative 4.247 times 10 to the negative seventh, and ejection fraction decimal is negative 7.95 times 10 to the negative seventh. Times 10 to the negative 2. Our adjusted R squared value was negative 0.0081, which means that the predictor variables, ejection fraction, and creatine phosphokinase, and platelets all have very low correlation with the creatinine serum levels. So going back to our multiple regression, we're going back to our multiple regression slide. So for the sodium levels, using the same prediction data set, the lower and upper bounds are between 128.16 and 145.39. We can predict with 95% confidence that the sodium serum level will be around 136.77, as you can see in the fit under the fit, using ejection fraction, platelets, and creatine phosphokinase levels as the predictors. And going back to the others, this slide. Okay. Our intercept for this regression is 1.334 times 10 to the second, and our coefficients for creatinine phosphokinase is 3.006 times 10 to the negative fourth. Platelets is 2.159 times 10 to the negative 6, and ejection fraction decimal is 6.538, as you can see. Our adjusted R squared value was 0.0279, which means that only around 2.8% of the variability in sodium serum levels can be explained by the multiple regression model, with ejection fraction, creatine phosphokinase levels, and platelets as our predictor values. While this value is still low, meaning our predictors have low correlation with our response variable, it's noticeably higher than that of creatine serum levels. And let me go to the next slide. So now moving on to logistic regression. So here we're trying to predict whether someone will die or not due to heart failure, a binary outcome by using ejection fraction, creatine phosphokinase levels, platelets, creatinine serum level, and sodium serum level. So we're just predicting about that. So we converted our logistic regression model into an AIC model, actually, which deleted several variables that the criteria deemed insignificant. Only ejection fraction, creatinine serum level, and sodium serum level were left for our predictor variables after running step AIC. For our prediction data set, we made ejection fraction equal to 0.4, creatinine serum level equal to 1, and sodium level equal to 140. And then with these values as are the predictors, the odds of someone dying is approximately 19.54%. Next slide. Over here, based on the coefficients, you guys can see under the coefficient slide, the odds of someone dying from heart failure increases as creatinine serum levels increase, while other predictor variables are held constant, meaning this does play a role in impacts the chances of someone dying. At the same time, as sodium levels and ejection fraction increases, the odds of dying decreases. So it's like a relationship. So in conclusion, even though a multiple regression model didn't have a strong correlation between response and predictor variables, our logistic regression model is actually very useful for predicting mortality. As you can see, it could be especially useful to doctors or just people who think that they're at risk of heart failure and death to see how urgently they need treatment based on the prediction, which is why I think this was a great, important project or important topic that we focused on. And thank you very much.